Okay, welcome to class. This is week 9, I believe. Is that right? We've got one more meeting after this one. So that means spring's almost here, I guess. Who's excited about that? Just one person? Yeah. Do you guys like my beard? Yeah? Okay, good. Says the guy wearing a beard. Some people are giving me a hard time about it, so I said I'll just ask my stats class what they think. And so what do we have this week? We've got chapter 12, which is all about what's called regression analysis. So I'm going to talk about that a little bit, and I'll try not to go too long. I went too long in the last class, so I'm going to try and tone that down a little bit, and then we'll answer questions about homework 7, which is due this week. So before we jump into regression, let me just say that I sent an email out about extra credit, and I just want to clarify on that. On Blackboard, there's a folder with Learn Smart assignments for each chapter. And if you complete those, you can earn up to 1 percentage point extra credit on your final grade. So I will calculate your grades according to what it says in the syllabus, and then if you do all of the Learn Smart stuff, then you'll get 1 full percentage point added to that. Now, it's not enough to take you from like a C- to an A, but if you're close, you know, it might bump you from an A- to an A or something like that. So, measure your level of performance so far and determine if you want to do that. But that's 1% for all of it, not for each one, not for each of the assignments, but for all the assignments. So if you only do half the assignments, then you get half a percentage point of extra credit. If you do a tenth of the assignments, then you get 1/10%. Okay. Yeah, that's Learn Smart. The due date for those is the 19th of March, which is a Monday, and you have till midnight. The exam is the next day, the final exam. So use that to help yourself study if you like. So regression analysis. Regression analysis is actually a pretty complex tool or set of tools that at some point you're going to learn more and more about. For now, we're going to stick with what's called simple linear regression. And simple linear regression is based on the same straight line formula that you learned when you were in high school, y equals mx plus b, except for we're going to write it a little bit differently. We're going to put the intercept first, and we're going to call it beta 0, and then we're going to add to that the slope, which we call beta 1, times x. And since this is statistics, and we've learned about random variables, and we've argued over the past 9 weeks or so that there's always some sort of inherent randomness or error, we're going to add that in, and we're going to call it epsilon. Okay, so the idea behind regression and any sort of model that you're going to run into is to explain the variation in the y variable. Right, so this is the variable that we're interested in, and we want to be able to explain the information that's contained in that variable. So imagine if there were no relationship between x and y, and we just said y is normal with mean mu and standard deviation sigma. Well, we know about normal distributions, so we should be able to find probabilities associated with that. But if I wanted to estimate mu, what's my best guess for that? Not X bar, but Y bar, right? Because now we've just changed the name of our random variable. But yeah, you're in the right, head in the right direction. So I'm going to say mu is, I'm going to estimate that with Y bar. Is my estimate right? No. So what do? I add and subtract z times sigma over the square root of n, and I get an estimate for the average value of the y's with some confidence. I get this interval. Okay, so if y has no relationship with x, this is the best I can do in terms of estimating the parameters for the average value for y. All right, everyone with me on that? This is what we did in chapters 8 and 9. Well, 9 we did the hypothesis testing last week, and the homework questions that we'll look at today are along those lines. Okay, so basically what we're saying is that there is uncertainty or variation in the y variable. And we want to use that in order to get an understanding about how our estimate's going to go. Is that door closed over there? Oh, you might get that. Thanks. Oh, never mind. You're already up. Okay. So variation is an interesting thing, and we've made arguments already in class that one source of variation is randomness, is uncertainty. In fact, we said that is always present, and what quality does it have? What can we not do about that? We can't estimate it. We can't explain it. We can measure it, and we can get an idea of how big the variation is, but we can't extract the information from the random part. So the idea with regression analysis is to say, well, hold on a second. There's a lot of variation, or there might be a lot of variation in the y variable. Some of that, above and beyond the random part, might be information. It might be informative. So if I can come up with a relationship between x and y, I should be able to do better in terms of estimating the y variable. And if that's the case, then I want to use this regression line. And if it's not the case, then I want to use Occam's razor. You guys ever heard of Occam's razor? Who's not heard of Occam's razor? Okay, who's not seen the movie Contact? So the movie Contact came out like, I don't know, probably before some of you guys were born. In the 90s, was it the 90s? Yeah, late 90s, something like that. Really cool movie. It's science fiction. Jodie Foster, Matthew McConaughey, a bunch of other big name actors are in it. And so Jodie Foster's the scientist, and she has a whole bunch of telescopes that are pointed in space, and she's looking for who knows what in the background noise of space. And one day she comes upon this signal that's kind of embedded in the background radiation in space. And they're like, wait a second, that's interesting. And they came up with some new technique or something to analyze data, and they get this signal, and it repeats itself every 3 or 4 days. You're like, what is going on? What is this? What is this signal? So they try and decode the signal, and it's coming from outer space. So this is like the first contact, that's why they call the movie Contact, that Earth has ever had with something not from Earth. And they can't break the code. And so this engineer, who's a genius and a billionaire and is very eccentric. In fact, he's sick and he's dying, but he's got so much money that he built himself a space station, and he lives in space because the zero gravity helps with his whatever sickness is or whatever. But he comes along and says, hey, I'm smart, I'm an engineer, I can probably help you with that. And sure enough, he breaks the code. And it turns out that this signal is the design, the blueprints for this machine that will open the doorway to the space-time continuum. And it's this giant sort of machine that has, I'm not doing it very much justice here, but they've got this big set of hoops like this. There's, I don't know, 3 of these things or 4 of these things. And there's like this little pod, a little station up here at the top. And somebody gets into this pod and they drop the person. Once these rings get spinning fast enough, they drop the person in the pod through the middle of that, and there's like a vortex created inside these rings, and it's super high energy, and you know, it's got to be made out of the space age material, and so Jodie Foster gets to be the first one to go through this. Well, the machine is so complex it costs $1 trillion to build. This is back in, you know, the late 90s when $1 trillion was really something. And so they build one, and of course there's outrage, outcry from the public, and they don't like it. Just, you know, don't mess with those things. And so they say, okay, well, just to appease everybody, we'll open it up for a public tour. And so the public comes in, and they're up here in this little pod place, and one of them's wearing a vest full of dynamite and blows himself up and destroys this $1 trillion machine. And so they're like, oh man, that sucks. What are we going to do now? Well, it turns out the first rule of government spending is why build one when you can build 2 at twice the cost? So they build another one in a different location that they didn't tell anybody about. And it uses so much electricity, it costs $1 billion just to turn the thing on. And so Jodie Foster gets up here, and she's in the little pod, and she drops through it, and immediately she goes back to the place where she grew up in Florida on the Panhandle, and her dad's there, and her dad died when she was little, but it's her dad, and she's able to talk to him and ask all these questions about, you know, what is this machine and what are we doing here, and she like kind of goes all over the universe. And 18 hours later, her pod comes back, and they have like a big net here, and it gets caught, and they open up the pod and they say, what went wrong? What happened? And she's like, what are you talking about? Went wrong? I saw my dad, and I asked all these questions to travel around the universe. 18 hours, it was awesome. They're like, 18 hours, what are you talking about? And they show her the video footage, and it shows her just falling straight down there. She doesn't go anywhere. It takes like 50 seconds, tells you how big this thing is. And they're like, wait a second, what's going on here? We just spent $2 trillion plus $1 billion to turn this thing on. We're upset. The American public are upset. Everyone's upset. Everyone in the world, everybody had to pitch in on this thing. And so they get her in front of Congress, and they say, look, we got 2 explanations. One is this crazy story you told us about going to see your dad and getting this signal from space and decoding it and all that. And the other explanation is that this is just some elaborate hoax. I mean, you got a signal from space. The guy who decoded the signal, where does he live? He lives in space, right? So you built this giant machine. The guy who decoded the signal, he's the owner of the construction company that built the machines, 2 of them, trillions of dollars. And so what's the best explanation? And they ask her, they say, what, you're a scientist, Occam's razor. And she says, yeah, okay, Occam's razor says, all else being equal, the simplest explanation tends to be the correct explanation. And so they said, okay, we got this elaborate hoax, or we got this crazy cockeyed story that seems very unlikely, and so you tell us which one's simpler. And of course, they're trying to get her to say, okay, it was a hoax and so forth. But she sticks to her guns, and that was actually part of the government cover-up, because they secretly wanted to still use this machine. They just didn't want taxpayers knowing that they were still turning it on. And so at the very end, she leaves the congressional hearing, and so they sent this this video recorder with her, so she could record everything. And the electromagnetic field inside of this big sphere killed the machine. It didn't allow anything to be recorded. And so, you know, somebody brought that up. The congressman brought that up, and they said, "Oh yeah, well, it did record 18 hours of static." So there's the proof. And the point of all this, that big long story, is that all things being equal, the simplest explanation tends to be the best explanation. But if you have evidence that suggests otherwise, then things are not equal. And in that story, of course they covered it up, but that 18 hours of recording of static is proof that things are not equal. Okay, so if things are not equal, then the more complex explanation is better than the simple explanation. In other words, if there's a benefit that you derive from having this complex model, or this complex relationship, right? This is a relationship between x and y. If that actually does something, helps you understand what's going on with the y variable better, then it's worth it. I mean, think about it. Has anybody ever been in a relationship? Yeah, okay. Are relationships complicated? Yeah, they are. Are they worth it? I think most people think they are, at least for a while. The simplest explanation says there is no relationship. So you want to go to the movies on Friday night. Is it worth it for you to go on a date or with friends or whatever? I mean, even if it's not a romantic relationship. Well, it's more complicated when you go with other people, because you got to agree on the movie, you got to agree on what you're doing before and after, and then you've got to get everybody there on time, and it's just, you know, can get to be very complicated. So you have to ask yourself the question, is it worth it to have this relationship? And if not, then Occam's razor says, just go to the movies by yourself. Right? You get to pick, you get to do everything all on your own. It's not complicated, it's just simple, and you just do it. That's exactly what we're talking about when it comes to regression analysis. And in fact, we can see that we can test the null hypothesis that beta 1 is equal to 0. So we learned about hypothesis testing last week. We learned about confidence intervals the week before. All of that comes into play here, and it allows us to test whether the complex relationship is worth it. Okay, so the null hypothesis says it's not worth it. If beta 1 is equal to 0, what does that mean about that term? Doesn't matter what x is, multiply it by 0. Okay, so that's the null hypothesis. That says there's no relationship. By the way, that's exactly the same thing as saying that the correlation between the two variables is 0. The alternative hypothesis says that beta 1 is not equal to 0. So if we have a null hypothesis, what else do we need in order to do a hypothesis test? We need a test statistic, we need an alpha level, we need a critical value, we need a p-value, and so forth. So it turns out that if I want to estimate, let me write it again. So y is equal to beta 0 plus beta 1x plus an error term. If I want to estimate beta 0 and beta 1, I'm going to get something that looks like this. And I call it y hat. That's the fitted value. It's b0 plus b1 times x. And in order to get the best values for B0 and B1, I have to define the criteria that I'm interested in, and there's something called the least squares criteria, which tells us when we solve for B0 and B1, there's a formula that we get for that. I'm not going to write it down. But this is going to be our estimate. B1 is going to be our estimate for beta 1. Just like x bar is our estimate for mu, s is our estimate for sigma, p is our estimate for pi, and so forth. So if I take B1 and I subtract the hypothesized value of 0, and I divide it by its standard error, so I'm going to write that S of B1. Again, I'm not going to write down the formula for that. It's in the textbook if you want to see it. For everything we do in class, there's going to be formulas or output that's generated, or we'll use Excel to get these things. That turns out to have a t distribution on n-2 degrees of freedom. So this is similar to what we did with the one sample procedure when we didn't know what sigma was. And we said, let's take x bar minus mu divided by s over the square root of n. That had a t, random variable, or t distribution with n-1 degrees of freedom. This has n-2 degrees of freedom. Why is it 2? Because now we're saying we have two parameters, beta 0 and beta 1, that are being estimated. So we lose an additional degree of freedom. In the case of the sample mean, we were estimating just the sample mean, so that was one parameter. And in fact, you can say if y is normal with mean beta 0 plus beta 1x and standard deviation sigma, you can see what's really going on here is that we're estimating the mean value of y as b0 plus b1 times x. So if you give me a value of x, I'll tell you what you can expect y to be. Give you the mean value of y. And it's a function of x. So if b0, if beta 0 is 1, that means, if beta 1 is 0, I said that backwards, didn't I? If beta 1 is 0, that takes out that part. B0 turns out to be just y bar. Okay? So, so that's what's going on here. You can think of it in terms of, if I've got data that looks like this, if there is no relationship between x and y, then my best guess for y is y bar. Just like that. Well, look how much variation there is in the data. It goes from here all the way up to here. So if I took this and said, let me take the sum of y minus y bar and square that and divide it by n-1, what is this? That's the sample variance. Or if I take the square root of that, I get the sample standard deviation. So that's saying there's no relationship between x and y. It kind of looks like there's a relationship between x and y here, doesn't there? Yeah, it does. If I draw that line in there, does that fit the data better? Does that explain what's going on a little bit better? Well, yeah, because now I can put these error bounds like this, kind of similar to what I had before. And this distance, if I sum up all these things, which is going to be yi minus, that should have an I on it, minus y hat. If I square that and take the sum of that, divide by its degrees of freedom, take the square root, I get a different estimate for the error that's in the data. And this new estimate, if there's information there, will be smaller than the other one. what we're doing with regression analysis is really testing whether this error sum or this error using the regression line is less than the sample standard deviation. So it turns out these are both estimates for the standard deviation. If they're roughly the same, if SE is about the same as S, then that means there's no relationship. So don't make things complicated, just forget about the X. It's exactly the same thing as saying beta 1 is equal to 0, and that means there's no relationship. If it's statistically different from 0, then there is a relationship. Okay? So does that make sense? Is that cool? Yeah, that's cool. If you don't know what's cool, that's cool. Why? Because let's say we have the price of a house, and that's equal to y, and we write y is equal to beta 0 plus beta 1 times x. What might x be equal to? You guys are going to graduate from college eventually, and you're going to get jobs, you're going to move off, and you're going to want to buy a house. So you want to know how big of a house, or how much the price of the house is going to be. So what could I use to estimate the price of a house, or to help me understand the price of the house? So the size of the house. So if I said x is equal to the size, okay, that's pretty, yeah, that makes sense. Does that make sense? The bigger the house, the more material it takes to build, the more time it takes to build, the more land that you have to have. So that would be a good candidate. But the question is, what is beta 1? In other words, if I increase the size of the house, what does that have? What kind of effect does that have on the cost of the house? Does that make sense? All right. What other information might I use in order to estimate the price of a house? I've got the size, but what else could I use? What other variables have a relationship with the price of a house? Okay, so the age of the house maybe. So I'm going to put a 1 here. I'm going to say x2 is the age of the house. Well, guess what? I can just keep doing this. And I'm never going to get rid of all the error, all the randomness. There's always going to be some sort of randomness, so I got to put that error thing on there. So this is something called multiple regression. We're not going to talk any more about it in this class than what we do right now. But I wanted to point it out because it's based on what you're learning with simple regression. And it's extremely powerful, extremely useful, and you will no doubt see it other places as you go into this data-driven economy that we now live in. But you have to be a little bit careful and apply Occam's razor here. Because what if one of these other variables was number of bedrooms? And maybe x4 is number of bathrooms. And x5 is number of cars can fit in the garage, and so forth. Turns out there's a lot of variables you could put into this model, and if you put enough variables in, you could explain all of the variation in the y variable. But if you do that, then you're doing what's called overfitting, and you're predicting randomness. Didn't we say that's a no-no? We did say that's a no-no. Don't ever try and do that. If you have a model that can explain everything, that means you've overfit. It means you're pulling stuff that has nothing to do with what's going on, and you're using that. And if you try and use that model for prediction out of sample is going to be horribly wrong. So apply Occam's razor here. If there are a lot of bedrooms, how's that related to the size of the house? Is it related to the size of the house? Sure. If you have a lot of bedrooms, it's got to be a big house. So there's redundancy in the information there. So you would look at that and say, well, let's throw one of these variables out because the information's already contained in the other variable. And variable selection's an important thing that you'll see some other time. But you will see multiple regression when you get to stat202. So look for that. Okay, so one other thing we need to talk about, something called the R-squared value, and this is otherwise known as the coefficient of determination. And this says of the total variation in the y variable, how much of that is explained by the regression line. And so let me draw one more picture. I'll make this one a little bit more simple. If we have these data points, and this line is our fitted line, so y hat, and go back to red. So here's y bar. Y bar is the worst fitting, y hat, y bar is the worst fitting line that there is in terms of squared error. So what do I mean by that? I mean, if I come to this point right here and I say, what is the distance between these 2 points? This is going to be y minus y bar. And if I take y minus y bar and I square it and I add it up, I get what's called the total sum of squares. What I'm doing is I'm saying how far are each of the data points from y bar. I'm squaring that distance and adding it up. That's going to be as bad as it gets for any line you could imagine. Now, it just so happens that that's what we use when we do a one sample procedure to estimate the standard error, right? Or to get the sample standard deviation. In other words, what we just wrote down, S is SST divided by n minus 1, and take the square root of that. And that says there's no relationship between x and y. That's as bad as it gets. Okay, well, what's going on with the regression line then? The regression line says, let's take this distance right here and write that down. It's going to be y hat minus y bar. And if we square it and add it up, we're going to get y hat minus y bar, quantity squared. That's called the regression sum of squares. So that's the amount of variation in the y variable that is explained by the regression line. Now what's left over, let's get a different color. You tell that's purple. What's left over is y I minus y hat. And if we take that and square it, yi minus y hat, and sum those up, we get what's called the error sum of squares. And that's what we're going to use to estimate the random part of what's going on here. Okay, so the R squared value is going to be the SSR, the regression sum of squares, divided by SST. And it just so happens that SST is equal to SSR plus SSE. So I can write this as 1 minus SSE over SST. So all it's doing is saying, given the total variation, what proportion of that is explained by the regression line? And it's going to be some number between 0 and 1, or 0 and 100% if you think of it as a percentage. And so you want your R squared to be as big as possible. given that you're not overfitting. In other words, Occam's razor needs to be applied here.
What's the standard deviation?
Which standard deviation?
Square root of stat divided by n minus 1.
Oh, so this is exactly the same thing as what I wrote right here. That's the sample standard deviation of the y variable, independent of any other variables. Right? We learned that. We looked at this formula way back at almost the very beginning of class.
We don't care about x.
Well, we do care about x, but this SST is the biggest the variation can possibly be. So then we're going to compare, we're going to say of that total variation, how much does the x variable tell us? And that's where this SSR comes from, right? Because y hat, this is the summation of y hat, which is b0 plus b1 times x minus y bar. So that part has the x in it. It's saying of the total variation, how much is explained by the x variable. Okay, so that's what's going on with regression analysis. Think of this as just a movie trailer, get you excited about it. Now go watch the videos, read the book, make sure that you're up to speed with the other stuff that is in the week 10 folder, week 9 and 10 folder on Blackboard. Okay? So questions about any of this? No? All right, well, let's move on then and talk about homework number 7. So questions from homework number 7. I'm sure somebody wants to see number 16 is my guess. So I'll put that one out there. But what else have we got? So homework 7 is due Thursday night. Quiz 7 is due Friday night. And then there's only one more homework. And that's due next Thursday, and no more quizzes after this week. There's no quiz on regression yet. It will be on the final exam. Okay, so should we look at number 16 first then? Or you want to look at some of these other ones first? Has anyone done the homework yet? You have any questions on it? No, okay. You got a question on it? Haven't started, okay. All right, well, let's look at, actually 16 is a little more involved than some of the other ones. So let's look at number 4 to start with. Okay, so this question says the mean arrival rate of flights at O'Hare Airport in marginal weather is 195 flights per hour with a historical standard deviation of 16 flights. To increase arrivals, a new air traffic control procedure is implemented. In the next 30 days of marginal weather, the mean arrival rate is 196 flights per hour. Okay, so they give us the data. We can look at that if we want. We don't actually need it for this question, because they've told us everything we need to know. The mean is 196. The standard deviation is, the sample mean is 196. The population standard deviation is 16. So I'm going to use a Z for this. So the first part says, set up the right tail decision rule. The alpha equals 2.5%. to decide whether there is a significant increase in the mean number of arrivals per hour. So is there an increase in the number of arrivals per hour? Historically, the mean was 195. We took a sample, and what did we get from the sample? 196. So does that mean it's bigger? And that's at the heart of hypothesis testing. Yeah, we observe something that's bigger. 196 is bigger than 195. So should we just conclude that it's bigger, it's changed? Well, it's hard to answer that question because what we're really asking is that a big difference? And if it's a big difference, then yeah, we'll reject the null hypothesis and make the conclusion that there has been a change. But if it's not a big difference, statistically big anyway, then we're going to say the difference we saw is just due to randomness. So what do you guys think in this case? If you had to make a guess without actually plugging anything in, is that a big difference or is that a small difference? 195 versus 196. Doesn't seem that big to me. But here's the point. You never can tell unless you do what? You look at the variation, right? What's the variation for x bar? We know the standard deviation is 16. So that's sigma. What's the square root of n? Square root of 30. That's somewhere between 5 and 6. So we'll have to plug it in and determine if that's big or not. Let's come back over here. And number 4, we have the null hypothesis says that mu is less than or equal to 195. The alternative says that mu is greater than 195. Why do we have that as our alternative hypothesis? Well, the question says, has there been a significant increase? So increase means bigger than. So in other words, is mu bigger than 195? That tells us that the null hypothesis is that mu is less than or equal to 195. So D is the right answer on that one. And so we should draw a picture. If you can draw the picture correctly, life's good. Here's our rejection region, and we have alpha, in this case, is 2.5%. So we get 0.025 right there. And so what are they asking us? Set up the right, okay. So in the x bar world, we have a mean of 195. In the z world, we have a mean of 0, and the critical value here is 1.96. So 1.96, that's the point that has 2.5% of the area to the right of it. And if we convert that number into the x bar world, what do we get? 195 plus 1.96 times sigma, which is 16, divided by the square root of n, which is 30. Okay, so for the first part, they just asked us to set this up, so we did that. Part B says calculate the test statistic. Now the test statistic could be in the x bar world, or it could be in the z world. Usually when they say test statistic, though, they mean the z world. And you know, if it's 196, it's in the x bar world, there's the test statistic right there. And rest assured, they're not going to just ask you to copy and paste that. What they're looking for is if x bar is equal to 196, we want z, which is 196 minus 195 divided by sigma over the square root of n. So I'm not sure what that number is. Let's come over here to Excel and work 7.4 mu 0 of sigma n else do we have? X bar, alpha, and we have the Z critical value, we got the X bar critical value, and oh yes, they want us to calculate the Z test statistics, so we'll call that Z calc, or you call it Z test, whatever you want. So the value of mu is 195, sigma is 16, n is 30, x bar is 196, alpha is 0.025. The Z critical value is going to be the value that has alpha to the right of it, so I'm going to get that by norm.s.inverse 1 minus alpha, that has 1 minus alpha to the left of it. So to get my x bar critical, I'm going to take mu 0 plus z times sigma over square root of n. So critical value is 200.72. So am I going to reject the null hypothesis? No, I'm not. What did I observe? I observed 196. That's clearly not in the rejection region. Okay. Still, they want the Z critical value, or a test statistic, so I'm going to take x bar minus mu 0 divided by sigma over the square root of n. So my test statistic has a Z value of 0.34. So I'll come over here and cut and paste that. So what's the conclusion? We already said we're not going to reject the null hypothesis because why? Because our test statistic is not in the rejection region. So there's not been a significant increase. So sometimes that's a relief, actually. If there's been a significant increase, what does that mean? They have a new method that they should implement because it's going to make things better. So they say. So if the test statistic's over here in the rejection region, that means we're going to reject the null hypothesis, which says that the new method, so we're comparing the new method to the old method. So if the new method's not any better than the old method, we're going to stick with the old method because everybody already knows how to use that, and there's no additional training that needs to go on. We don't have to shut anything down, and it's just, don't have to print any new procedure manuals. What's that? Yeah. Yeah, and what did we see? We saw 0.34. Yeah, here's a. So there's no significant increase. Part B3 doesn't really make sense. Would the decision have been different if you used alpha equals 1%? I mean, that part makes sense. They give two conflicting arguments here. One says yes, one says no. Just ignore those. Just answer the question. If alpha is 1%, then Z is 2.33, and so instead of 1.96, you'd have 2.33, which is way out here. That's even further out in the tail, so you're not going to reject then either. So let's say the result is not any different. What kind of assumptions are we making? I don't really like this question because it says 30 is the number of observations that we have, and the central limit theorem says if the number of observations is 30 or more, then you don't have to worry about what kind of distribution you have. But if you say that, you'll get it wrong. So put normal population, or at least one that is not badly skewed. And then click on that and get it all right. Okay, so let's do one more question before we do number 16. So number 13, is this one I want to do? Yeah, okay. Now let's do, let's do 13. To combat antibiotic resistance, you guys know what that is? Everybody gets sick and then they go to the doctor and the doctor says, oh, just take some antibiotics. And then you take the antibiotics and the bacteria that the antibiotics are supposed to kill mutates, and the antibiotics don't kill it anymore, and then that spreads, and so that's a big problem, and it comes partly due to the fact that doctors are giving out antibiotics like they're candy. So to combat that, the Quality Improvement Consortium recommends a throat swab to confirm strep throat before a physician prescribes antibiotics to children under 5. A random sample of 55 children who received antibiotics for throat infections, 18 did not have a throat swab. At the 5% level, is this a significant reduction over last year's national rate of 40%? Okay, so this question, I don't know if it entirely makes sense or not, but you can tell what the alternative hypothesis is here because they're asking, is there a reduction? What does reduction mean? That means less than, not less than or equal to. So the alternative hypothesis should be that mu is or pi is less than 0.4. So that means this should be the right one. Okay, so whatever 18 out of 55 turns out to be, I guess that's going to be, that is going to be less than 0.4. So I guess maybe this does make sense. I don't know if it makes sense or not. But that's how it's set up, and this is what we're testing, whether pi is less than 0.4. I mean, it seems to me if they're trying to get people to swab before they prescribe, wouldn't they want the percentage to go up, not down? Anyway, that's, I guess, a philosophical or fundamental question. So that's the correct null hypothesis. Calculate the critical value. So let's come back over here. This is homework 7.13. We have the null hypothesis that says that pi is greater than or equal to 0.4. And the alternative says that pi is less than 0.4. We have alpha, so alpha is 5%. We have P is equal to X over N, where X is 18, N is 55. And what else do we have? So they want a critical value. So here is null hypothesis. The alternative is true in this direction, which means our rejection region is going to be down here. If alpha is 5% in the Z world, what value has 5% of the area to the left of it? That's going to be negative 1.645. And is that what they're asking us? I think that's what they want, although the other alternative would be taking 0.4 minus 1.645 times the standard deviation, which is 0.4, square root of 0.4 times 1 minus 0.4 over n. In this case, n is 55. So it's either of these two things. I'm going to start out with the first one and just plug it in and see. Say negative 1.645. Okay, so that is what they're looking for. Calculate the test statistic. The test statistic is going to be in terms of z. So z is going to be equal to p minus pi 0 divided by the square root of pi 0 times 1 minus pi 0 over n. So in this case, that's 18 over 55 minus 0.4 divided by the square root of 0.4 times 1 minus 0.4 divided by 55. So let's go over to Excel. Plug all these numbers in. 7.13. We have pi 0. We have x, n, p. We have alpha. And we have z critical value. And z calc. So pi 0 is 0.4, x is 18, n is 55, p is equal to 18 divided by 55. So the sample proportion is 32%. We're comparing that to 40%. Are those different? Obviously they're different. Is the difference big? That's the question. What do you guys think? Is that a big difference? Maybe. Practically, it's a big difference. Sure, 8%. The question is whether it's statistically different, or there's a statistical significant difference. So alpha is 0.05. So our z critical value is going to be equal to norm.s.inverse. Just put in alpha because it's a left-tailed test. So there we get the negative 1.645. Our z calc is going to be equal to p minus pi 0 divided by the square root of pi 0 times 1 minus pi 0 divided by n. So we get a calculated test statistic of negative 1.10. So what did we see? We saw here negative 1.1. So is it a big difference, what we expect and what we saw compared to what we expect? No, it's not a big difference. You know, it's 8% or 7.5%. It's not a big difference. So we're going to reject the null hypothesis. Nope, we're not going to reject. Fail to reject because we're not in the rejection region. Is it safe to assume assume a normality of the sample proportion p? Yeah, it is, because we have 18 successes and we have okay, now that I read this again, I guess this does make sense, but they kind of goofed it up. So 18 did not have a throat swab, and last year it was 40%. So they're actually saying they still have it backwards. But anyway, we have 18 out of 55. The rule of thumb for the central limit theorem with proportions is you have to have n times pi and n times 1 minus pi both be bigger than 5. And this textbook, I think, uses bigger than 5. Some say bigger than or equal to 5. But 18 is bigger than 5, and 55 minus 18 is bigger than 5. So say yes. got it right. Good job. Okay, so let's look at number 16 now. And then unless you guys have more questions, we'll wrap up after this one. Unless you want me to keep talking, I can talk for another hour if you want about regression more or whatever else. But let's look at this one. A quality expert inspects 370 items to test whether the population proportion of defectives exceeds 2%. All right, so what's going on? They have this process, they're making something, whatever it is that they're making, they pull it off, and they look at 370 items, and they're measuring what proportion are defective. So they've got this process that's, when it's tuned in and dialed in right, it's producing 98% or more non-defective parts. Okay, so the null hypothesis here is really that the machine or the process is working like it should. They're saying pi is less than or equal to 2%. The alternative says that pi is greater than 2%. So if it's bigger than 2%, then they're going to say, well, hold on a second, there's something wrong going on. Let's stop the process. Let's figure out what's going on and fix it. And when it's fixed, then what? Then we're going to produce defects that are not that, within the specifications of what we would like. So n is equal to 370. Alpha is equal to 1%. And so here's the interesting part. Part A says, what's the power of the test if the true proportion of defectives is 4%? So let's draw the null. Under the null hypothesis, we've got this picture. 2%. Right? And if alpha is 1%, that means there's a rejection region up here. And now the rejection region is fixed. The rejection region, remember, is determined by alpha and the null hypothesis. Okay, so what's going on? They say, what if the real value is this number here, 0.04. If that's the real value, then we have this distribution. And so the power of the test is what? It's the probability of making the correct decision when the alternative hypothesis is true. So it's this area in red, or the red distribution. So given the alternative hypothesis is true, what's the probability you're going to make the right decision? That's the same thing as saying, what's the probability you're going to reject the null hypothesis when the alternative is true? And in this case, we're saying the alternative is true, and the probability of, the value of pi is 4%. Okay, so to answer this question, we need to know what the critical value is. And the critical value is, again, determined by the null hypothesis and the alpha level. So this is going to be 0.02 plus the value that has 1% of the area to the right of it is what? 2.326, I think. 2.326 times, let me write this down here, critical value 0.02 plus 2.326 times the square root, 0.02 times 1 minus 0.02, all divided by, in this case, n is 370. So whatever that critical value is, that's going to tell me when I reject the null hypothesis. That's the value that has 1% to the right of it under a standard normal. The z value, yes. Unless I'm off, it could be 2.57. I think it's 2.
It is.
What's yours? What's your alpha level? Oh, 5%. Okay, yeah. So yours is gonna be 1.645. So you can get that. So we'll come over here, plug this in. 0.16. We have pi 0. We have n. We have pi 1. We have alpha. Let's see, what else do we need? So the critical value, we're going to need that. So under null hypothesis, we have pi 0 is 0.02, n is 370. Again, it's 370. Did I get that right? 370. Pi 1 is 0.04. Alpha 0.01 for mine. So the critical value, we'll put it as the z critical value is going to be equal to norm.s.inverse 1 minus that thing. So 2.326, and we want the p critical value, right? So the p critical value, that just says take this value of whatever it turns out to be 2.326 in the z world and convert that to the p world. So we're going to do that by I'm going to insert I only want to type this once, so I'm going to say this is equal to call it p pi 0 STDEV. So standard deviation of p is going to be equal to the square root of pi 0 times 1 minus pi 0 divided by n. And maybe that's not the best name for that. I'll just say it's p, standard deviation of p, given the null hypothesis. All right, so we're going to need that, and then too many. Okay, so to get this p critical value, I'm just going to take pi 0 plus z times, instead of typing it all out again, I've already typed it once, I'm just going to do it one time. All right, so this is just the standard deviation. This is the square root of pi 0 times 1 minus pi 0 over n. Instead of doing that every single time I need to call it, I did it one time. So my critical value is 0.0369. 0.0369. So I know the mean under the null hypothesis. I know the mean under the alternative hypothesis. That means I know the mean and the standard deviation. Sorry, that means I know the standard deviation under both, and I also know the critical value. The critical value is never going to change. It's based on alpha and the null hypothesis. So I'm going to reject whenever I get a test statistic bigger than 0.0369. So in order to find the power, all I have to do is say, given the mean of 0.04, now what's the area under the curve to the right of 0.0369? And we know how to do that, right? This is just standard normal stuff now, or normal stuff. Yeah. So which one do you want to look at? So this p standard deviation. I really should put, let me put it under, let me put p0. So that's signifying under the null hypothesis. Or maybe, yeah, right. And I guess actually I do want one more. So under the alternative hypothesis, I have P1 times 1 minus P1 divided by N. Okay, so if the null hypothesis is true, then the standard deviation of P is this number, 0.007. The alternative hypothesis is true, and pi is equal to 4%, then the standard deviation of P changes to 0.01. So I have to take that into account. It doesn't change my critical value, but if the alternative hypothesis is true and the proportion is actually bigger, then that means the standard deviation is going to be bigger too. The bigger that proportion is, until you get 50%, the bigger the standard deviation is going to be. Once you hit 50%, it's going to start falling off again. Okay, so all I need to do is find out the probability being bigger than this number, 0.0369, when the mean is 4% and the standard deviation is about 1%. So I'm going to first of all calculate the z that I'm going to use for the power. This is going to be critical value minus pi 1 divided by standard deviation of pi 1. So my z value is negative 0.3. So negative 0.3, 0.1. So I want to know what's the probability that z is greater than negative 0.3011. That's the power. So I'm going to calculate that using 1 minus norm dot s dot dist. Put in the power, comma 1, and we get a power of about 61%. And let's just check the work. So is that the end of the question? No, they're saying, what if the proportion is actually 5% instead of 4%? Now calculate the power. So this is how you calculate what's called a power curve. You could say, let all the values of pi that represent the alternative hypothesis being true, let's plug those in and see what the power of the test is. And in other words, this is saying, if the true value is 5% versus 2%, what is the chance that we're going to pick that up, given the sample size that we have? So all we have to do for that is come over here, copy, and paste. Okay, and now I'm going to change pi 1 to 0.05. And when I do that, notice that the standard deviation changes a little bit, but everything else stays the same. The critical value stays the same, and but our z value changes. So now instead of having, so what we're doing when we do this is we're now shifting out here to the right, Right, with green. Now we're going out here and saying here's 0.05. Now what's the area under the curve? And so this now becomes negative 1.15 under the green distribution. And the power then is 87%, so I didn't draw that picture very well, but that's okay. And then finally they say, what if it's 6%? So if I have a sample size 370 and the true value of pi is 6%, what are the chances I'm going to pick that up? Reject the null hypothesis. Well, my the z value is now negative 1.86, and the probability of making the right decision, and the alternative is true, is almost 97%. Okay, so you could use this type of analysis to say, do I have a big enough sample size? Because what if it's really important that we pick up 3%, for example? Well, what's the power if pi 0 is 3%? Let's see. So I could just put a whole bunch of these things in here. The last three are the ones that I want. Let's just put those right there in the middle. And let's change this to 0.025. So at 2.5%, 0.03, 0.035, 0.04, 0.05, 0.06, and then let's put in 0.07. Of course, they didn't ask me to do all this, but let's just look what's going on. If the true value is 2.5% instead of 2%, what are the chances I'm going to pick that up? About 7%. So that's a pretty small probability. And you can see if the further out I go, the bigger this gets. So I could change the sample size if I want. Let's put in 1,000 here instead. If I have a sample size of 1,000, now what's the chance I'm going to make the right decision if the true value is 2.5% versus 2%? I can come over here and the power has doubled for the case when pi is 2.5%, but when pi is 3%, now I'm up to 47%, 3.5%, 80%, 4%. True value is 4%, I'm at 94% power. So you could come in and say, okay, do we really care about differentiating between 2 and 2.5%? Maybe not. Practically, they're basically the same. But the difference between 2 and 4%, we want a high power test for that. So we can change alpha, we can change beta, we can mess around with these things. And that's going to allow us to determine how big our sample size needs to be in order to meet the specifications that we are after. Okay, and all that's business, related. You got to have expert or domain knowledge in order to answer that question. How big does it have to be, or do we care about practical differences of certain size? Okay. Other questions from this homework? Nope. Okay, then I will stick around here until nobody's here or 150 comes around. So if you do have other questions and you'd like to talk to me, feel free to do that. I will be in my office from 2 to 3. You can come there as well. And otherwise, we will see you guys a week from today.
Hi, I have a question about this one. Is it not that we just look at the table?
Sorry, let me see. It says, using the appendix, find the p-value for each test statistic. Okay. So if it's a right-tailed test, you have z value is 2.21.
Yeah, so let's 2.21 is 0.464.
So this, hold on, let's draw a picture. Always draw the picture. So z is equal to 2.21. So here's 0, and here's 2.21. Now the empirical rule should tell you